In this video, I will be presenting on multi-heuristic A star, talking about the background of the paper. So, the performance of the heuristic-based search algorithm like A star depends heavily on the quality of the heuristic functions. If the heuristic function is not properly drafted according to the application, the performance degrades heavily. Now, for many of the high-dimensional applications, it is difficult to include all of the complexity of the problem in the single heuristic function. As a result, the performance degrades drastically, and there will be occurrence of large depression region in the search problem. Now, the depression region is the region where heuristic value does not correlate well with the actual cost. Hence, the search algorithm, which includes more than one heuristic function, can be used, which includes all of the complexity. This is where multi-heuristic A star is beneficial. So multi-heuristic A star considers multiple arbitrarily inadmissible heuristic function to perform the search, and it also uses a single heuristic function to ensure that the algorithm is complete. Now it uses all of these heuristic to perform search simultaneously. This inadmissible heuristic guides the search through the depression region, and it will make the conversion faster because normally the single heuristic function may get stuck in the depression regions. Now the search performed using the heuristic admissible or a consistent heuristic is called anchor search, while all other searches is called inadmissible searches. So it uses two variables or two weights to control the search. W1, which is similar to what it's used in A star, it basically inflates the heuristic, and W2, which prioritizes the inadmissible search over the anchor search. All the value of the weight W1 and W2 is generally higher than 1. Consider a problem statement shown in figure A. Here, a PR2 robot needs to grasp the object placed on the table. The object is surrounded by different obstacles. There are two paths shown. The blue path is generated using a single heuristic function, while the red path is generated using a single consistent heuristic and multiple inadmissible heuristic. If the robot follows the blue path, it will be on the left side of the table. The obstacles are placed in such a manner that if the robot will be on the left side, it won't be able to grasp the object. This information is not included in the single consistent heuristic, while the path shown in the red color is obtained using a single admissible heuristic along with multiple inadmissible heuristics. So single uh, admissible heuristic can guide the robot along to the goal destination, and multiple inadmissible heuristics can include information such as the location of obstacles, so that after the robot is in the near to the object, it will check whether the configuration is hitting any obstacle or not, and it will be successfully able to grasp the object. There are two variants of multi-heuristic A star proposed in the paper, named independent multi-heuristic A star and shared multi-heuristic A star, which will be discussed further. Independent multi-heuristic A star uses individual cost to come and heuristic value for each search, so it uses its own priority queue. Here, the search is performed for n plus 1 times, in which n times is performed for inadmissible heuristic and 1 for the anchor search. So the state is expanded for n plus 1 times. Also, it runs the inadmissible search in round robin manner. Let's now take a look at the pseudocode. It uses three functions to perform the search. Key function is used to calculate the cost of the state. Expand state is used to explore the node. Once it gets the node, it removes it from to the particular open list. Then it will add all the neighbors to the successor. If the neighbors are not expanded before, then the cost will be assigned as infinite. As now they are expanded, the new cost will be assigned as the cost to come of the previous node and the cost to travel from previous node to the current node. This node will be inserted in the queue of the particular search if it has never been explored previously. Now the main function is where initialization and the search happens. For initialization, it will initialize it for all search including anchor search. It will take the empty queue as a open queue, and it will also take a closed list. It will assign the cost of the start to 0 and cost of the goal as infinite. Back pointers will be set as null. Then it will add a start node in the queue of every search. Then it will perform a while operation until the goal has been reached or there are no nodes to explore. For each inadmissible search, if the weight is if the weight prioritize uh, inadmissible search, then it will prefer the inadmissible search to perform the exploration. If the goal hasn't been reached yet, then the node will be taken from the inadmissible search. Then it will be expanded using expand state function and inserted into the closed list of the particular search. Now, if the weight W2 doesn't allow to perform the search using inadmissible heuristic, then the node is been taken from the anchor search. It will be expanded and inserted into the closed list of the anchor search. If the goal state has been reached and the cost of the goal state is less than infinite, then the algorithm and the while loop is terminated and the path is being returned by backpointer. The other variant of multi-heuristic A star is called shared multi-heuristic A star. It uses different heuristic values to perform the search but only uses a single cost to come value. In shared multi-heuristic A star, a state can be expanded at most twice. Also, the current path obtained by the search is shared among all other searches. So, to reach the goal, the partial paths obtained by different search can be used. Let's take a look at the pseudocode. The key function and the initialization part is similar to that of independent multi-heuristic A star. However, shared multi-heuristic A star uses only a single cost to come variable and backpointer variable to store all the cost of each search. Also, the shared multi-heuristic A star uses two closed lists, one for the anchor search, another for all inadmissible search. The key difference lies in the expand state function. So, if the state has already been expanded and added to the closed list of the anchor search, it will not be expanded again in any of the searches including anchor search and inadmissible search. However, if the state has been expanded in any inadmissible search, it can be expanded again into the anchor search. That results that the state can at most be expanded twice in the search. Also, the last condition in the expand state function makes sure that none of the state are added into the open queue of any inadmissible search such that it won't be expanded again in the main function. The main function is similar to the independent multi-heuristic A star, and it will use each inadmissible search in round-robin manner to perform the search. Also, it uses a weight W to prioritize the inadmissible search. If the goal path is generated, then the search is terminated and the path is returned by the back pointer. The manipulation planning for the PR2 robot example shows the advantage of multi-heuristic A star over single admissible heuristic search. Figure A suggests a problem statement where the robot is required to grasp a large object and traverse through a narrow corridor and the doorway. So the blue configuration shows the initial configuration and the green configuration shows the goal configuration. Figure B shows the vector field generated by the backpropagation. In figure C, the robot uses a single admissible heuristic to traverse the path. However, it does not include any information of the orientation, due to which it gets stuck at the doorway. Now, to rectify this problem, the goal orientation and the vertical orientation heuristics are uh, incorporated into the algorithm. Now, figure D and E shows that these algorithms and heuristics are implemented separately. Now, these have their own depression regions, which makes the robot to get stuck at different depression regions depending upon the heuristic used. However, as shown in the figure F, where all of the heuristics, including the admissible base distance heuristic, the goal orientation heuristic, and vertical orientation heuristics are used together, the robot is used to navigate successfully from the start or initial location to the goal location. The multi-heuristic A-star is compared with different algorithms for several application domains, which will be discussed in further slides. Comparing several algorithms for PR2 manipulation planning. Here, the problem statement is described earlier. The admissible heuristic is considered as the maximum distance of the end effector or the base of the robot from the goal. For inadmissible heuristic, two randomly selected points from the base circle around the goal is selected, which has the valid inverse kinematic solution that can be reached by the robot. For another inadmissible heuristic, the orientation difference between the current state and the goal state is calculated. The results are shown in table 1. Said multi-heuristic A star and best for search performs better than independent multi-heuristic A star, as they both can use the partial path obtained by previous searches. Also, multi-parameter weighted A star performs slightly better than weighted A star, which shows that the depression region can depend upon the weights used to derive the algorithm. Also, best-first search performs comparable to said multi-heuristic A star in terms of numbers of instances solved and slightly better in terms of convergence time. However, the solution cost obtained are significantly worse than multi-heuristic A star in general. These algorithms are then compared in multiple goal planning scenario. The problem statement comprises of planning in a multiple goal environment. Here, the objective is to plan to any of the goals from the given set and generate a plan. Such planning can be assumed in an autonomous car in a parking scenario where there are multiple parking spots and the car needs to plan to any one of the parking spot. Here, the multi-heuristic A star runs in two modes: multi-heuristic A star admissible and multi-heuristic A star inadmissible. In the former mode, admissible heuristic is used for anchor search, and for inadmissible searches, an individual heuristic is used for each inadmissible search. In this later part, For all inadmissible search, the outer radius based inadmissible heuristic is used. Further, there are two search techniques that are used to compare against multi-heuristic A star, known as sequence A star and mean A star. In sequence A star, the path to each goal are individually calculated, and depending upon the minimum cost, a path is selected. In mean A star, a single heuristic is created for each state by calculating the minimum distance across all goals. This is the comparison of the results. Here, the results are shown as the ratio between the given algorithm and the corresponding sequence A star values based on the runtime for the convergence. Multi-heuristic A star inadmissible performs the best, and this difference increases with the increase in number of goals, as it takes the advantage of multi-heuristic approach to perform the individual search, and if any one of the inadmissible search reaches the goal state while satisfying the bounds, it can successfully terminate, while other algorithms can stuck in the large depression regions. All algorithms perform similarly in terms of solution quality. And this ends the presentation. Thank you.